In this next part of the talk, I will try to give you ways to provide a better answer. So let's say we're going on a trip. Okay, so first you need to know where you want to go. Okay, let's choose randomly. I don't know, pick a country, France. I don't know why I chose that. So once you know where you want to go, so this is going to be your idea. Then what you're going to do, you're going to look at a map. Okay. In synthesis, we are going to use similarly a kind of map that we call a binary or a ternary or more phase diagram. So these are going to be our maps. And we're going to use the maps in the same way as a real map. You're going to use it to decide how you're going to travel. Is there a border with the ocean? Then you can go there by boat, or are you going to go there by plane? We're going to use those maps in the same way to decide how we're going to do the crystal growth. How am I going to try to get a single crystal of a certain material? Am I going to be able to use solution growth or vapor transport? Something like this. And so since this is a tutorial, I will tell you where we get those maps. Okay, most of them you can get them online for free at this website from HFM International. This is their nice building that has a huge dome of honeycomb lattice. This is the headquarters in Ohio. And so I will tell you a few tricks about how to read those maps. Okay, so we're going to take an example. This is a binary phase diagram of silver and barium. So at the bottom axis here you have the composition. So here is 100% silver, and then here is 100% barium. And then the vertical axis is going to be the temperature. So for every composition and temperature, you are somewhere located on this map. Okay, on this binary phase diagram. And you can see that at high temperature, as you expect, you have a liquid phase. And the border of this liquid are those lines here that we call liquidus lines. And basically, these are very important for solution growth, for example. And below these lines, you will start to have not just one liquid phase, but a multi-phase system. Typically, one solid and one liquid. So below this liquidus line here, you start to have two phases. Now you can see other things on this example phase diagram. For example, you can see this compound here, barium. I'm going to use this way, this side here is going to be easier for me. Barium, silver 5. You see this compound has a width of formation. So that means that there is a certain range of composition that this compound can exist. So not just exactly barium and silver 5, but barium, silver 5.1 or something like that. When you can do chemical substitution, you also have a range of a width of formation like this. But the other compounds in this example, they are 9 compounds, so they don't have a width. They have a very well defined stoichiometry. So for example, barium silver 2, barium silver, and barium 3 silver. Now another thing you can see on this example phase diagram is there are 2 compounds that actually reach the liquid state here with a maximum in the liquidus line. Okay? This type of compound are called congruently melting compounds. So what this means is that you will melt the compound from an homogeneous solid to a homogeneous liquid. Many materials are like this. For example, water is like this. You have ice that melts at 0 degrees into liquid water. Right? So most elements, actually all the elements and compounds like water, they are congruent. Congruently melting. If they don't sublime, like acid. Now, other compounds, not every compound are like this. The other 2 compounds in this example, barium silver and barium 3 silver 2, they don't melt, they decompose. Okay? So what happens is that they decompose, barium silver decomposes at 560 degrees here into another solid and a liquid. So many compounds actually don't melt, but they decompose when you warm them up. And then there are other features on this phase diagram. I will mention one last more that is important for crystal growth techniques. And those are minimums in the liquid region. So you can see local minimums. I've shown 3 of them in this example phase diagram. We call that a eutectic point. Those are local minimum in the liquid regions. And you know that already. For example, when you put salt into water, so this is the diagram, for example, for water and salt. When you put salt into water, you decrease the freezing point of water, and you use that to remove the ice on the street in winter. At least in France we do this. In California, never do it. And you can do this. The more you add salt, the more the freezing point is going to decrease. But there is a limit to that, and this limit is minus 21 degrees. Below minus 21 degrees Celsius, then you can add more salt. The freezing point is not going to reduce anymore, and that is the eutectic point for this diagram here. And sometimes they can be very deep. So another example here is the phase diagram for gold and silicon. Gold and silicon, they melt at quite high temperature, above 1000 degrees Celsius for gold and silicon. But at some intermediate composition, you have a very deep eutectic, so that means that in this composition here, the system is going to melt at only 360 degrees Celsius, so much lower than the melting point of gold or silicon when they are by themselves. And those are very interesting for technical solution growth, because then we have a huge range of a liquid to perform solution growth. Another very good example of this is the system boron and platinum, where these two compounds, they melt at extremely high temperature, above 1700 degrees Celsius, and there is a quite deep eutectic also on this composition, where they melt below 800 degrees Celsius. Now, okay, that was just a background on how to read those phase diagrams. Now let's do a real example. Let's try to grow something. And I'm going to choose to illustrate this with how to grow a single crystal of manganese bismuth. Okay? Why would you want to do this? Well, manganese bismuth is a simple binary compound, so it's good for a tutorial. But also, it is a ferromagnetic material with a very high Curie temperature. And in fact, it has something very peculiar. The magnetic anisotropy of this material increases when you increase temperature. Most compounds, the magnetic anisotropy decreases when you increase temperature, but this one, the magnetic anisotropy increases. And also, it's a very uniaxial magnetic anisotropy, and so that means that you can use this compound to make permanent magnets, for example. So let's try to see if we can figure out how to grow single crystals of this compound just by looking at this mark here. So this is again a binary phase diagram where on the left you have pure manganese, on the right you have pure bismuth, and the compound manganese bismuth is here at the 50-50 composition. And this compound, you see, doesn't melt, it decomposes. It decomposes at 355 degrees Celsius. It decomposes into another compound that we call the high temperature phase of manganese bismuth, and a liquid phase that is rich in bismuth. And so this means that manganese bismuth is not melting concurrently. And so in terms of synthesis, that means that if I would be to mix manganese and bismuth in a 50-50 composition and have at high temperature a liquid state, if I just pull it down, I'm going to first get a crystal of manganese, then a crystal of the high temperature phase of manganese bismuth, then a crystal of manganese bismuth, and then pure bismuth. So I'm going to get a crystal that has 4 phases inside, so truly bad quality crystal. so instead, we're going to use this phase diagram to decide to use an excess bismuth to start with. So we're going to start here at this composition. That is marked by a red cross here, for example. That is somewhere around 90% bismuth. And I have represented here what you would have typically in your crucible. You'd have in red atoms of manganese, and in blue a large excess of bismuth. Now, as you cool it down, you're going to reach this liquidus line here, and so you're going to enter into the two-phase region. That means you're going to start to have a small crystal and still a large excess of liquid. So I'm cooling down here, and I start to form a small crystal of manganese bismuth in my liquid. And as you keep cooling down, you're going to have more and more of this crystal and less of this liquid. And in fact, you can see that the liquid is less and less containing manganese, so it's richer and richer in bismuth. And you can read this composition by the red arrow indicated here in this phase diagram. Okay? So then, just before we reach this eutectic point here, if we keep cooling down below the eutectic point, everything freezes. But just before it freezes, we can remove the excess liquid, and then we have just a nice and shiny single crystal. Okay? So that is how you would use the basic principle for what we call solution growth technique to get single crystals of manganese bismuth. Now that's in theory, right? That's all the concept I get from reading the phase diagram. But now I have my strategy. I'm an experimentalist. I want to go in the lab, and actually I want to do it, right? So what I'm going to start to do is just I'm going to take pieces of manganese, pieces of bismuth. I'm going to use a simple scale, weigh them to get the proper ratio. I want somewhere around 90% bismuth and 10% manganese. And then I'm going to put everything into a crucible. And because I know at the end I want to get rid of the excess liquid, I'm going to prepare for that. So I will use a frit, like kind of a filter, that I will put on top of the crucible. So I put all my material here in this bottom crucible. I put a filter, and then I put another crucible on top to just catch the liquid later on. Okay? And then we're going to seal this into an ampule. And why we do this is because we will want to avoid to have air reacting with my material. Because if I have air, I will form manganese oxide or bismuth oxide, and that is not what I want to do. So here you're going to have to learn how to work with silica, and basically we are going to neck down the silica tube. This is what you see here in this video with the hydrogen oxygen torch or just a gas oxygen torch. Then we're going to purge, remove the air, replace it with isovacuum or replace it with argon, something inert, and then you get your sealed ampule. Then we're going to put this into a furnace. So this is, in my lab, all the furnaces, they have a name. So this one is Snowy. And we're going to leave it here, the ampule that is sitting in another crucible so that it stand up upright. And we leave it in the furnace, and we warm up to get a liquid region, and we slow cool so that we grow the crystals slowly in the furnace. And then before we get to this eutectic region, before everything is going to freeze, we want to remove the liquid. And so what we're going to do, we're going to take the ampule out of the furnace, and we're going to dump it into this centrifuge. Then the centrifuge is going to push the liquid through the filter, through the frit on one side, and the crystals are going to remain on the other side. And so this way, I've separated my excess liquid, and now I have nice and shiny single crystals. Now we do this, we have to do this at high temperature because we have to do it before everything solidifies, right? So don't try to do this at home. Okay, this is done by a professional. She's an undergraduate student with 1 week of experience. And so you use this technique that is a solution growth, and you can grow many kinds of crystals. Manganese bismuth. You can even try to do substitutions by adding other elements into that and reproducing the exact same synthesis. Actually, when you do this, sometimes you get surprises. Here we actually found a new crystal with a completely new structure when we try to draw it on the slide. And you can go also other compounds, iron-based superconductors, other kinds of 3D ferromagnets, but basically a very, very rich and very simple, rather cheap and very versatile technique for crystals. Now, since this is a tutorial and I only have 1 hour, I cannot cover all of the details. Of course, there are many other technicalities to know about this technique that I don't have time to talk about, in particular how you go from this example of a binary compound to a more complicated case of ternaries or quaternaries and other things you need to know about. But basically, you can grow many kinds of crystals, and they are nice, and you can take shiny, nice pictures of them. They are cute looking. I love them. And you're welcome to use this technique. It's one of the easiest techniques out there. And using this technique, in my young career, I was able to contribute to many fascinating topics of quantum matter. You can find new compounds sometimes, you can find new superconductors, you can study iron-based superconductors, spin reorientation, quantum criticalities, and so on. Okay, let's now look at another example. I'm going to ask you this question: how would you grow this compound, uranium germanium 2? So now I give you this phase diagram, a binary phase diagram where you have germanium and uranium, and the temperature, and you see this compound uranium germanium 2 is here in the phase diagram. It melts congruently at a high temperature of 1450 degrees. And you also see that it doesn't have a huge range of liquidus around it, because it is basically surrounded by these 2 other congruently melting compounds. And so that tells me that solution growth is not going to be a very good idea to grow uranium germanium. Instead, because uranium and germanium are melting at a high temperature and they have a low vapor pressure, a technique that is very good for this is what we call the Chopalsky technique. And so now I want to tell you about this technique a little bit, because it is a very important technique in terms of its influence on our work. So the Chopalsky technique, it's even simpler to understand. You're going to melt the materials, and then you're going to put in this liquid of molten metals, you're going to put a tip or something. This tip is usually colder, and so the crystallization will start on this tip, and then you're going to pull the tip vertically like this, and you're going to grow a crystal directly on your tip. And this is a very important technique, because this is the way that we grow silicon single crystals nowadays, out of which you're going to cut silicon wafers, out of which every single piece of electronics that you use nowadays is coming from, right? So one of the most important techniques, and you can see for silicon, they grow those massive single crystals of silicon that are basically taller than humans. And you can see also 2 features here. You can see the part where the crystal is attached here, so that is the tip, and the part where the crystal grew. And then also you can see this tail here. I will talk about this in a couple of slides. But before, I want to tell you about the man who discovered this technique, Jan Szokalski. This is a Polish scientist, and he found this technique just before World War I. Okay, so a long time ago. That was before the Apple pen. That was, in fact, before the pen. And so he was taking notes, but he was using a feather. And he was taking notes about his experiments using a feather that he would put in ink and then take notes like this. Now, while he was doing this, he had next to his pot of ink, he had a pot of molten metal that he had just taken out of the furnace. And so by mistake, instead of putting the feathering into the ink, he put it into the molten metal, realized his mistakes, put it up very quickly, and realized that you can go single crystal this way. Right? So that is an example of a very well-designed experimentalist knowing exactly what he was doing. Now, to melt the materials, you can use various techniques. You can use simple resistive heater, or you can use arc discharge, or you can use even induction heating. Now, for uranium germanium 2, because those are metals, okay, so it is possible to use arc, for example. So this is an example of what an arc furnace for a Szokalski pudding looks like. You have a crucible here and some material that you're going to put on the crucible, and you have 4 arcs here on the side. And out of those 4 arcs, we're going to create an arc discharge on argon gas that is going to create an argon plasma, and this plasma is going to heat and melt your elements. Okay? So you're going to melt the material by this argon plasma, and then in the middle, you're going to approach with a tip that you're going to pull vertically, and you're going to start to grow a crystal that you can see here out of this ball of molten liquid metal. Now again, that is nice, and this is the concept, but there is a few aspects to this. So again, you're going to start by weighing your material. So you're going to go back to the scale again and weigh uranium and germanium. This time you're going to use the exact stoichiometric ratio, so uranium 1, germanium 2. And then you can mix everything using a simple arc method, where you just melt when you don't pull first, to just homogenize, make a homogeneous crystal. At this point, it is a polycrystal, so you have many grains of your compound, but you don't have a single crystal. And then you're going to put this into the furnace, and so you want to first time you do this, what are you going to use as a tip to put inside? Well, you can use, first time you can use a tungsten tip, for example, out of which you're going to pull a crystal. But later on, you can use this crystal as a seed for the next synthesis. So you can use this seed, and you can even orient the seed along a particular axis of growth. So this technique is really nice because you can control the growth direction with respect to the crystallographic structure. And so, for example, here you have a seed that was oriented so that we can grow the next crystal out of a specific direction. But when you put the seed into this liquid, you don't control the crystallization. So you're going to get many small crystallites that are going to form on this seed, and you're going to lose partly the orientation. And so a small trick here, I'm going to just mention 2 of the tricks for this technique. The first one is what we call the necking. So you're going to pull the crystal along a certain for a certain time by keeping the diameter of your crystal rather small, and the hope, or even you can try to reduce it. And the hope during this process is that you have many grains that formed during the quick crystallization, and one of them is going to grow larger than the other, and the others are going to are going to disappear, or are going to become smaller and smaller. And so the hope is that we start to get just one type of single crystal in this process. And then after that, you can reduce the power into your furnace, and you can start to grow a larger diameter single crystal. And so you're going to do this. Here I'll show you two examples where you have the necking here, and then you grow the crystal for several centimeters. And this is just one big single crystal that is several centimeters long. So if you do neutron experiments in elastic, you want this kind of crystals to do the measurements. Now, as you can see, and I've mentioned it before, there is also a tail before the crystal is finished. Now, this is part of another trick. Why do we do a tail at the end of the synthesis here? Well, what happens? Yes.
Do you leave the tip inside the solution, or do you just pull it out?
So the question is, do I leave the tip inside the solution, but then I pull it out?
Or just leave it?
If you leave it in there, then nothing's going to go, right? Because you get the power, you get the ball of liquid, and you have a tip inside, that's it.
And how fast?
Oh, yeah, good question. So how fast do we grow this, for example? This is maybe, typically a cooling rate is like 20 millimeters per hour. So you get a couple hours here to grow this. So you can grow this in a day. And then, so why do we do this tail at the end? Basically, what happens is that you have this crystal that is inside the molten metal, and so it is getting heat from the bottom, and this heat is diffusing around the crystal. When you're going to stop and detach your crystal from the molten liquid, you're going to lose this input of heat all of a sudden, and that can put strain in your sample due to a thermal shock, basically. And you can have strain that's going to create defects, and you want to avoid this. Sometimes this can even be dramatic, and this can even break the crystal during the synthesis. So because of the thermal shock, you get this huge contraction that can break the crystal. Okay, yes?
Is it also possible as you put for crystals out of the solution because of the thermal gradient and the possibility of phase diagram?
Right, so the question is this possible to get other phases as you put the crystal? And so this is a good point. In this example here, I'm using a case of uranium-2 where the system is congruent. That means that the composition of the liquid is the same as the composition of the crystal. So I am removing from the melt a crystal that has the exact same composition. So at no point during this process, the composition of either the crystal or the liquid is changing. But obviously, this only works if my crystal is congruent. And so that is why, like I said, there is not one technique that works for everything. But this works for every kind of materials that are going to, this might work for every kind of material that are going to be congruent. And in particular, pure silicon, for example, is a case where you don't have to worry about getting other different compositions. And so mostly I've used this technique to grow uranium compounds, and just with this narrow range of compounds, you can already touch very interesting kind of physics. For example, there is a hidden order state in uranium, ruthenium, silicon 2. There are this kind of compound, uranium copper germanium or uranium germanium 2, where you have coexistence of ferromagnetism and superconductivity. And and this is something very interesting to look at. And many of the things that you can get access to as long as you get samples using this technique. Quantum criticality again, very large apocritical field, thermoelectric materials, and so on. Now, again, you know, this is only a tutorial of 1 hour, so I don't have time to cover everything about this, and also I don't have time to cover every single technique out there. In particular, I don't have time to cover the loading zone technique, which is a very important one, but also the Bridgman method, chemical transport, and high pressure synthesis, or even electrochemical synthesis as well. Now, this is the end of my first part about crystal growth. Actually, I forgot to ask you before a question: who has already grown a crystal here? 4, 5, 6, 8. 8 minus my 2 students over there. Okay, so that is more than I expected. I'm quite happy to see I'm not alone here. Now, let me ask you another question. How many compounds do you think we can make? And actually, let me rephrase this. How many compounds do you think have been discovered? So I mentioned, what did I mention? Manganese bismuth, uranium germanium 2, pure silicon, and other ones. How many are there out there? So we're talking about inorganic materials. 700, 7,000, more. I have no idea.
50,000?
50,000. Really good. Yeah, in fact, there are around 70,000, more than 75,000 compounds that have been discovered already. Inorganic compounds, and I'm talking only about stoichiometric compounds, so not like small substitution or something like that. And you see that rate has been pretty much constant since the 60s, and that means that every single day there are 4 new compounds that are discovered, mostly by chemists. And when I ask chemists the same question, they don't know the answer either. They don't even come close like you did. And we can even go further. Out of those 4 compounds that are discovered every day, 3 of them are either ternaries or quaternaries. And so what this means is that the technique that we're going to have to develop to make single crystals of those compounds are going to become more and more involved. So I will argue that just the small number of people here who have made crystals before is not going to be enough to catch up. Okay? So that's why I'm teaching you this. Please come and help us. We cannot do it alone. Okay? There are way too many systems. And I know you only care about magnetic stuff, right? So I made a small, recently I was interested in chromium compounds. So I look at chromium compounds. This is the place where you would expect to find magnetism. Inorganic chromium compounds. And I made a selection. I selected, I select binaries and ternaries because I did not want to have to design a way to deal with quaternaries. And I decided I don't want anything that has another magnetic element in it, so no iron, no cobalt, no other valence elements, just chromium as the only magnetic stuff. And then I selected a subset of structures that I can consider tetragonal, octagonal, and hexagonal. So I remove cubics and other monoclinic, triclinic stuff. And then I get a list of compounds, already discovered compound that is about 339, actually exactly 339 stoichiometric chromium compounds. And I looked at all of them, what's known about them. Some of them are ferromagnetic, some of them are anti-ferromagnetic, but then most of them, and by most I mean like look at this diagram here, almost all of them, nothing's been measured on this material. So not only we get new compounds every single day that are popping up, but the ones that are already known, they are far from being characterized. And this is just chromium, okay? I can do the same with manganese, I can do the same with iron, copper, nickel, copper, and then all those various elements here. So this is endless, right? So welcome to quantum matter physics. You're never going to be out of topics for your research, right? So I will conclude this first part now. I hope I can convince you that it all starts with crystal growth. There is not just one technique that works for everything. That's kind of unfortunate. And there is a huge potential for new discovery in our business. Now, the second part is about how to kill magnetism. And so I will argue why do you want to do that? I will argue that if you want to understand something, you can first understand how it breaks. Okay? Or in other words, if you want to understand how a car works, you dismount everything, remount everything, and then you're going to be a good mechanic. Right? That's what they do in the army as a training. They dismount a jeep, remount a jeep, then dismount a jeep, remount a jeep, and again and again. And so I'm going to try to see what happens when you suppress magnetism in systems. And I'm going to choose a system, a magnetic order that is the simplest. I'm just going to choose ferromagnetism. Okay? Nothing overcomplicated, not a frustrated system, just simple ferromagnetism. What happens when you suppress ferromagnetism in a system? And this topic has to do with quantum criticality. So, and for ferromagnetic quantum critical. So what is that? You have a paramagnetic state and a ferromagnetic state, so you have a transition that is of the second order between the two, and you tune this transition so that it happens at 0 Kelvin. And you do this using a tuning parameter, which can be pressure, chemical substitutions, or magnetic field. And then you have a second order phase transition that happens at 0 Kelvin, and that's what we call a quantum critical point. And so people have studied this, and I'm just going to give you two examples of this case, zirconium zinc 2, for example, and uranium germanium 2, which we just talked about how to make crystals of these. So both of those compounds are ferromagnetic, and if you apply pressure for both of them, you can suppress the ferromagnetic transition. Now, did we find a quantum critical point here? No. In fact, we don't. In fact, we can track the transition approaching 0 Kelvin, but then it disappears all of a sudden. What happens is that the transition becomes of the first order. So in the phase diagram, there is what we call a tri-critical point, where the transition is going to change from the second order to the first order. So in zirconium zinc 2, this tri-critical point is at about 3 Kelvin, and in uranium germanium 2, it is at about 25 Kelvin. And then because the transition is of the first order, near 0 Kelvin, it has an infinite slope. That is explained by the thermodynamic relation called the Clapeyron relation. And so you see that there is no quantum criticality because the transition is no longer of the second order, it is of the first order. And so the question is, why does the transition become of the first order? And people have considered that. There are several theories out there. One possibility is that the lattice, the magnetization couples to the lattice. And it was shown already a while ago that this can lead to a first order ferromagnetic transition. Another possibility is that you have a particular peak in in the density of states near the Fermi energy, or you have change of topology of your Fermi surface, and that is also possibly responsible in some case to a first order fermenting transition. And then one more scenario in theory is that you can have those systems are metallic, and so in the metal you have particle Hall excitations, and those couples to the magnetization, and it was shown that this will always make the transition of the first order at low temperature. And so that scenario actually looks like it's a general scenario that you can apply to many compounds, and it is based on the fact that you have like those particle Hall excitations that corresponds to long wavelengths correlation. That means a small, in reciprocal space, a small wave vector Q. And so near this quantum phase transition here, it is possible that those effects are becoming so large that you're going to have a new phase that is going to order with a small wave vector Q. And this has been considered also by several theories. And what they find is a new possibility for the phase diagram where you have this fermenting state here corresponding to Q equals 0, and then you have this new phase that has a small wave vector Q that can vary in this region here. It can vary with pressure and with temperature. And this new phase starts at a point that we call the Lifshitz point, and it can be like a spin density wave, or helical ordering, conical ordering, and so on. And so we already have mentioned two examples of this first scenario here, where the transition becomes of the first order, with zircon zinc 2 and uranium germanium 2. And so now in the next part, I will show you an example of this case here, which we found in the compound lanthanum chromium germanium 3. So this is a compound that you can grow out of solution growth with an excess of germanium, and you get single crystals of this material. This is a compound that has an hexagonal crystal structure, and it becomes ferromagnetic below Curie temperature of 85 Kelvin. And then it has an effective moment that is somewhat smaller than what you would expect for chromium 3+, and so that tells us that there is some degree of delocalization of the magnetism in this system. And also the saturation moment is 1.2 µm per chromium, and there is quite some large anisotropy in the system. The moments are aligned along the c-axis, and you have a quite large magnetic anisotropy. Now, once you have this, you can apply pressure to this, and first we did magnetization measurements and the pressure. And so you see when you measure magnetization and the pressure, you can track the fermenting transition, and it is suppressed at a pressure of about 2.1 gigapascal. And then we did also other kinds of measurements, in particular resistivity measurements, which is a simpler kind of measurement you can do under pressure. And we found we were able to track this transition, but we found another anomaly. That anomaly is like a bump into the electrical resistivity, and we can track this anomaly as a function of pressure, and it follows this green line here on the phase diagram. Then we did muon spin rotation experiments under pressure. This is a work we did in collaboration with Rustem Kasanov at the Polcher Institute in Zurich. And what we found is that when you enter this new region here, the internal field grows, and it is about the same as the internal field that you have in the ferromagnetic region. And so what that tells us is that this new region here is magnetic, because the internal field starts to grow when we enter this phase. And so we call it anti-ferromagnetic Q. Now, it is very difficult to know the Q vector under pressure, especially at this pressure above 2 gigapascal, and with this type of moments that are also rather small at the limit of what can be done. we've done already several attempts at neutron measurements, but so far we haven't been able to find the wave vector Q. But what we can do is we can look at what we expect from first principles time spectral calculation. And so here I will, so this is something we did with Carmine Bo's group at Iowa State University. And I show you here the enthalpy as a function of the wave vector Q. So Q equals 0 corresponds to a normal ferromagnetic state. Q equals 1 reciprocal lattice unit corresponds to a normal anti-ferromagnetic order, up, down, up, down, up, down. And then other values here corresponds to smaller values of the wave vector. And what you can see is that at low pressures, the most stable is the ferromagnetic state. And as we have mentioned just in the previous talk, in theory you can even do negative pressure, minus 2 gigapascal, and that confirms that the ferromagnetic state is the most stable. But if you go into the positive pressure side, then you can see that there are many states at low wave vector Q that are nearly degenerate. And within the resolution of what we can say from this type of calculation, we can basically say that any kind of wave vector in that range is going to be at a very similar energy, or even more stable than the ferromagnetic order. And so clearly, that seems to indicate that most likely this new phase has a small wave vector Q that is also in agreement with the recent proposals for ferromagnetic quantum criticality. And so you see we have now this example of lanthanum chromium germanium 3, which is a new compound that shows this type of phase diagram, where you have the appearance of a new phase, which is this kind of new way to avoid ferromagnetic quantum criticality. And the more conventional way is that the transition becomes of the first order at the tricritical. And so with two ways to avoid ferromagnetic quantum criticality, then that raises the question, is there no way we can find it in systems? Is there no way we can find ferromagnetic quantum criticality? And I will show you that in fact, ferromagnetic quantum criticality is still there, but just not on this slide. Okay? When you look for something that disappeared, you first go back to where you have seen it for the last time. So here we are looking for this second order paramagnetic ferromagnetic transition. And so the last place where we see that is at this tricritical point. And so you go back to the tricritical point, but then you need to search outside of the box or in a third dimension. Basically, I'm going to apply a third parameter here, magnetic field. And so now I go into a three-dimensional phase diagram where not only I have temperature and pressure, but now I have magnetic field as well. And you can see that starting from this tricritical point, there is this new line of second-order transition that decreases and eventually reaches 0 Kelvin, where we have now a new kind of quantum criticality. And because it is new, it is still under debate how we call that, either a quantum wing critical point or a marginal quantum critical point. Now this is the phase diagram experimental. We call this a wing structure phase diagram because of the symmetry. This one is the one for uranium germanium 2. And there is a similar phase diagram that was observed also in zirconium zinc 2. And other materials, manganese silicide, strontium riceinate, uranium cobalt aluminum, and so on. And so this was all summarized recently in a nice review by Brando, Kirkpatrick, and Belitz, where they basically summarize the situation with this two-phase diagram here. Either the transition becomes of the first order and you have a wing structure phase diagram when you apply magnetic field, or you have the appearance of this new type of magnetic ordering, And this new phase is going to exist under some range of magnetic field, and so you have a dome in the phase diagram like this of this new phase in the three-dimensional phase diagram. How much time?
That's about 55 minutes.
Okay. So, because lanthanum chromium germanium 3 has this appearance of a new phase, then we thought, okay, lanthanum chromium germanium 3 is going to correspond to this bottom case here for the phase diagram. But in fact, we realized that it does not correspond to this. We found a new possibility, which is basically a mixture of the two. So not only we found this dome of new magnetic phase, but also the existence of these wings under magnetic field. So because I don't have much time left, I will skip a lot of details, but this is the phase diagram that we get. Not only I skip details, but I skip a lot of helium consumption to get that. But you see in green this dome of new magnetic phase region, and then on top of this you have these wings here, the blue planes, that we can track up to 14 Tesla, which is the limit of our magnet, but then it extrapolates to a quantum wing critical point at much higher fields. So, to summarize this, we find this third possibility here, which is a mixture of the wing structure and the superconductivity and the new magnetic phase dome. Now, after we reported this phase diagram, then the theory, in particular Valentin and Kirkpatrick, they reconsidered in more details the effect of the magnetic field on this figure, and I will show you the results in the next slide. You have I will show you the t equals 0 plane, so the field pressure plane at t equals 0 for these two cases here. So on the left here you have this dome of new magnetic phase region, and again it is symmetric with respect to magnetic field. And for the case on the right, in addition to this region, you have this plane of first order transition that terminates at a quantum wing critical point at high field. And in their theory, they published last year, they were able to show that you can go from one phase diagram to the other when you increase the size of those quantum fluctuations. And so if we believe this, that means that lanthanum chromium germanium 3 is an example when we have the large quantum fluctuations. Now they also found an intermediate case where not only you have basically intermediate here, where you have the first order transition line that terminates within the dome of new magnetic phase. And so in this case you have a first order line that changes to a second order line at t equals 0, and so we call this a quantum high critical point. And in parallel, we were actually working on another material. That material has the same structure as lanthanum chromium germanium 3, but it is a cerium titanium germanium 3. And in that compound, the magnetism originates from cerium. And we actually found that this is an example of this intermediate situation here. Again, I'm skipping a lot of details, but this is the phase diagram that we found for this compound. It is ferromagnetic at ambient pressure. And when you apply pressure, you have these regions in this region in green of new magnetic phase, and you see the wing terminates within this region at a point, at the quantum high critical point that we estimate from experiments to be around 5.4 gigapascal and 2.8 Tesla. And in fact, there is just before we published this, a similar case was observed in another compound by the group in Cambridge. This is niobium iron 2. In this compound, you can tune the magnetism by changing the ratio between niobium and iron. And in the niobium-rich part of the phase diagram, they also found evidence for this quantum high critical point. So at this kind of point, you will have a divergence of not only the ferromagnetic fluctuations, but also the anti-ferromagnetic type of fluctuations. Now, to summarize this here, you see that, so going back to this slide with all the possible type of phase diagram, you see that compared to this review 2 years ago, we have significantly extended the range of possible phase diagram, and that with the feedback from theory is in pretty good, at least a qualitative agreement with the theory. And so I will conclude here. So now the second part of the conclusions for the second part. So with these two compounds, lanthanum chromium 3 and serum titanium germanium 3, we find new types, we find new phase to avoid quantum criticality. And you see that despite the fact that we have chosen to start with the most simplest magnetic ordering, ferromagnetism, you see that there is still a lot of unknown physics, or unexplored at least, and that it is actually rather complex. And so that is the minimum we can do before we try to attack other more complicated cases, like anti-ferromagnetic systems or competition between other orders and so on. So I will thank you for attention. But before I completely finish, I was given a couple slides for the food, which I know you're all super interested in. That's why I keep it for the end. So the options, so the lunch are provided by the parents, but today is the tutorial, so there is no lunch provided. And so for those of you who stays in the dorms, it is recommended that you try to use your tickets, food tickets at Segundo. I will show you a map in the next slide of where it is. And for the others, you can go to the silo, which is just next to this building behind the bike barn. And there is also a lot of good places downtown. And so this is the map here. So we are in this building here. The silo is just next to this building. Segundo is here on the north. And there is also food options at the Memorial Union here, or on 3rd Street downtown. There is also several restaurants, burgers, and wrap and all this. I think this slide here where you have different stores, restaurants on 3rd Street. Okay, thank you very much.